Welcome everyone to the January meeting of the Madison Astronomical Society, our first meeting of the year. And yeah, I apologize for, it's kind of a curveball for all of us, but here we are all at home, safe and sound off the roads, and there's lots of snow going on. And with all the snow in the news, especially if we have some newer people who might be interested in using our dark sky site, Yana Research Station, soon. This is just a quick reminder that we do not have snowplow service out there. So if you're going to head out and use Yana Research Station, prepare to bring a shovel and use it a bit. And also, I know from personal experience during the winter, even if the driveway is plowed off a bit, it's easy to kind of miss it a little bit and not see a divot. I've had my car stuck out there. So that's just something to be very careful of if you're like backing out in reverse or driving, just to be careful that you don't accidentally run off the driveway. Does anybody have any questions about Yana Research Station? I guess if not, there's a presentation coming up on the week of January 23rd at the Madison School District Planetarium there at the high school at Memorial High School on Tuesday, January 23rd and Thursday, January 25th. They are having a special presentation about the eclipse coming out called Lights Out, Eclipses, Whys, Wonders, and Wows. So yeah, if you're gearing up to see the eclipse coming up this spring, head out there. Last I looked, you do have to go online and get for Madison residents. You can get a ticket for $6, and non-Madison residents can get tickets for $9. It looked like they still had some openings available on the later show Tuesday night and the Thursday night shows. There's a 6 o'clock and 7:30 show on Thursday night, and then it looks like the Tuesday night show on the 23rd is still open at 7:30. So that sounds like that should be a good show. And I know Bob, when we were at Bell Burnell Observatory a little over a year ago, I think Bob, you might have been there, the new planetarium director that they have at Memorial. He's a really great guy and a really great teacher. So I encourage everyone to check out the planetarium this season. Also, we could do a little bit of a preview of next month's presentation. Our next meeting, hopefully in person, on Friday, February 9th. We are going to have Dr. Jesse Thwaites, a student at the UW Madison, will give a talk titled Chasing Ghost Particles, Searching for Neutrinos from High Energy Sources in Real Time. John, did you want to say something about that?
Yeah, Jesse is actually another graduate student. Bob, you probably know Jesse. Jesse's also a fourth-year PhD student, and as you said, she'll be talking about some real cool research using IceCube at the South Pole.
Yeah, and for those of you who have been maybe longer members of the club, in the past we've had other presentations about IceCube, and this is a observatory where somebody had a UW astronomer had the idea that you could basically turn a vast thick ice sheet down in Antarctica into a telescope, essentially, because he realized that the ice would be virtually transparent to neutrinos. So this is a really neat observatory down there that the UW astronomy department has some really leading the real leading efforts with. So it's really fascinating. So yeah, thank you very much, John. That sounds like a great talk. So does anybody else have any announcements that they'd like to share, or any observing experiences they'd like to share? If not, Bob, if you wanted to show us some pictures from the Bell Burnell Observatory, quick, go right ahead.
Sure. Let me share my screen here. So if you haven't been out there, this is the old student observatory and I guess MES observatory on the Promega campus. And this was dedicated last fall as the Bell Burnell Observatory. Joyce Bell Burnell was a graduate student who was involved in the first discovery of pulsars. And she was there in person for the dedication last fall, which was pretty cool. And you can see the 16-inch scope that was donated by one of the members, I understand. Is that correct?
One of our past members, yes, that is correct.
Yeah. And there's a Takahashi 4-inch refractor on top of it as a very nice guide scope. And I got involved about 2 years ago when they had fully refurbished and installed the scope, but there really wasn't anybody using it at the time. And one of the first images I took was of the Horsehead Nebula. And I've got that alongside a new Euclid image on the right to show you what a really outstanding picture of that nebula looks like. We had it up when comet C2022E3 passed by, and so we took a sequence of images and made the short movie out of it. We purchased a filter wheel and a bunch of different filters for it. But the narrowband filter we bought was an O3 filter, and of course the moon is so bright, it's nice to have something narrowband to image with. So this is just a shot of the moon. And July of 22, we had another comet that we imaged just passing across the star field a little bit more slowly. And then I'll be talking about looking for planets orbiting white dwarfs. And this is the one known planet that orbits a white dwarf. It's about a 16.5 magnitude star, so this is difficult to see. But on the right there, you can see that little smudge, which is an out of focus dim star, disappears in a couple of the images. And white dwarfs are so small that when a planet goes in front of them, it blocks all of the light and the star disappears for about 10 minutes. We imaged Saturn and thought this was pretty cool. We got down to seeing 5 of Saturn's moons. On the right there, Enceladus is like a 60-kilometer diameter moon orbiting Saturn that is one of the places where we might be looking for life in the solar system. So it was pretty cool to get down to that level of detail. I trained a group of Promega employees to observe there, and they took these pictures of Jupiter just last November. Don't know what's going on with Jupiter's moons there. I think we got a couple of stars involved because I've always seen them lined up much better than that. And this was kind of a cool observation. We observed asteroid Juno, and you can see it passing across the star field in a loop on the right. The light curve on the left shows the intensity of light coming from the asteroid in blue was increasing during the observation, and that is showing the rotation period of the asteroid as different surfaces with different albedos face the Earth. So that was kind of a cool observation we did. And what I do mostly there, I work with a group of undergraduate students, teaching them how to observe, and we do follow-up observations on exoplanet candidates using the telescope there. And this is probably our nicest observation, where you can see the dip in light as a planet passed in front of the star that's circled on the left. And using the depth of that observation and confirming the period between dips is very helpful to confirm some of the exoplanet candidates that scientists are looking at. So our team does this kind of work. And I think, oh, there's a couple more. Here is the constellation Orion rising over the observatory. Gives you a nice picture of what it looks like today. It's really outfitted quite nicely. And then we just had an event at the end of November where we took some pictures of the sun using my personal, I got a Dobsonian 10-inch that we took these pictures through. That's just an iPhone image. And that's it.
Well, thank you very much, Bob.
Do you
And
have anything else in the way of announcements, Lawrence, or do you want me to go ahead and give Bob a proper introduction?
I can't think of any announcements unless someone else can think of something they'd like to say or share. I give it a moment, and if not, we'll proceed.
Or if you want to do a welcome of visitors or new members.
Yeah, it's kind of hard to tell. Yeah, I don't know if there's anyone here who's visiting us for the first time at Madison Astronomical Society. Feel free to unmute and introduce yourself. I'll introduce myself. I'm Lawrence Moore. I'm the president of Madison Astronomical Society. I guess we're not going to have any takers. Going once, going twice, sold. All right. Well, with no further ado, John, would you like to introduce the speaker tonight?
Yeah, you've already had a chance to hear from Bob. Bob Aloisi is a PhD student. Bob, is correct to say you're fourth year or fifth year PhD student?
Fourth year.
Fourth year. Bob described himself to me as a non-traditional graduate student. You may be able to tell from his handsome face there that he's not your typical 22-year-old PhD student. Bob came back later in life after a career in a completely different area to go back to graduate school. And Bob principally studies exoplanets, and that's what he's going to talk to us tonight about. I do want to mention that since we're meeting with Zoom, we will have the chat window up, and you can, oh, I see that Adam chimed in there as a new member who can't really speak because he's sick tonight. So Adam, welcome to the group. I put a note up there that you can use the chat window to ask questions as Bob is speaking, and we'll be monitoring the chat window, and we will relay your questions to Bob during his talk. After Bob concludes, we'll have a little bit of time, maybe 15 minutes or so, where we can do live Q&A, where you can actually just unmute and you can ask your question directly to Bob. So without any further ado, we'll turn it back over to Bob and let Bob share his screen again. Bob, you might want to say a little bit more by way of introduction of yourself, and we appreciate you coming out on this snowy night to talk to us. Thank you very much.
Thanks for that introduction, John. And feel free just to speak up with questions as well. I will have no problem with that. And just to confirm that you guys can see my screen, and I'll get started. Thanks again. Again, I'm coming from UW Madison. I was a member of the Sheboygan Astronomical Society, attending a lot of meetings just like this when I was 50 to 53 years old. And made a life decision to go back to school and study astronomy full time. So now I'm in my 4th year at UW Madison as an astronomy PhD student. And my advisors are Andrew Vanderberg from MIT and Kei Zhang at UW Madison. One interesting thing about this image here on the right, I put the title of Searching for Planets Born in Unusual Places into an AI like ChatGPT window. And this is the image that it generated for me. So this is an AI generated image on that topic. A little bit more about myself. I do like school. I'm a lifelong learner. And I've done all of my schooling in Wisconsin. So I first got my degree in chemical engineering at UW Madison and got a master's in paper science, and then worked in the paper industry for 29 years. And then when I was about 53 years old and made the decision to come back to be an astronomer, I first got a second major in physics and minor in math at UW Milwaukee, and then applied to programs and fortunately got into UW Madison. I finished my MS degree and all my classes, so now I'm strictly doing research, and I'm in my 4th year. During work, I spent about 29 years developing paper products, things like wet wipes, Dixie cups, and paper towels. Got a number of patents doing that work, and got to the place financially and personally where I was ready to move on to new adventures and came back to school. One of the things I really enjoy is sharing my passion for astronomy, which I think I probably have in common with several of you. And one of the things that I do is use local telescopes to follow up on exoplanet candidates that were discovered using a space telescope called TESS that we'll talk about later in the talk. And I also do a lot of stargazing outreach. I do some of that at the Bell Burnell Observatory, which we looked at images of earlier. And I work with about 6 undergraduates doing the exoplanet observations using that telescope. UW Madison also does a Universe in the Park program, and I help coordinate that program. And we give talks like this around at different state parks during the summer months. So usually we like to start these talks with some motivation for why are we spending our lives doing this research? And in my case, there's some basic answers that we're trying to, questions that we're trying to answer, such as when did planets first start to form? And what types of planets formed around some of the earliest stars? And then flipping that around towards looking at the end of a star's lifetime, questions are, how long can planets survive at the end of a star's lifetime? And maybe could there be life around some of those planets or stars? I don't know if anybody's familiar with this chart on the left, but this is a typical way we talk about some of the planets that have been discovered. And to date, there's over 5,500 exoplanets that have been discovered orbiting other stars. All of them are what are called main sequence stars that are in the middle of their lifetimes. And this chart shows the period of those planets, how long it takes for them to orbit their star, and the mass. And looking at the different regions of this diagram tells us a lot about what kind of planets form and where they are in their own solar systems. So we know about all those planets around main sequence stars, but I like looking for planets around stars in unusual environments. planets that were born outside the Milky Way or transiting these older white dwarf stars. And the diagram on the right here shows the one only point for the only planet that we know of that orbits a white dwarf star. And what I'm trying to do is get a few more of the initial points on this plot on the right. So my talk today, I'm going to talk a little bit about the methods that we use to look for exoplanets. And then I'll talk about searching for planets orbiting white dwarf stars briefly, and then get into this search for exoplanets that were born outside the Milky Way. So the first method I'll talk about is the transit method. And this is just a little cartoon. You're looking face on down from the top of this little solar system, and then it rotates to edge on view, and you'll see this planet go in front of the star. And then the lower left, you'll see how the amount of light that we receive this from the star dips as the planet transits or passes in front of the star. And that's what we're looking at in this method. We'll see a periodic signal where the light will dip on a repeating frequency. The data that I work with is from a spacecraft called TESS, which stands for Transiting Exoplanet Survey Satellite, that was put in orbit about 5 or 6 years ago now. And what it does is it surveys the whole sky in sectors that are observed using 4 different cameras. They're tiled, so you get this image that's 24 degrees across by 96 degrees vertically or in latitude. And if you look at the image on the right, you can see how TESS is orbiting Earth in the center of a sphere there, which is the celestial sphere. And this tile of 4 images goes from the pole down to the ecliptic of the sky. And every 28 days, it rotates to a new part of the sky. So it observes the entire sky about every 2 years. It takes an image every 30 minutes in the initial program, and you can search those images, but you can also write proposals to get cutouts to search specific stars at more frequent cadences, either 2-minute or 20-second cadences, which can let you find a lot smaller signals from stars orbiting, planets orbiting different stars. The second method I'll talk about is called the radial velocity method. If you've heard of this, this is looking for the wobble of the star. And it's used by a spectrograph on a telescope called WIN in Arizona on Kitt Peak. And you can see a picture of that in the upper right. If I play this little cartoon again, we're looking edge or face on at a little solar system. And now you can see that as the planet and the star orbit each other, the star is going to wobble back and forth. And when it's coming towards us, the wavelength of light moves towards the blue wavelengths. And when it's moving away from us, it moves towards the red wavelengths. And what you get for a circular orbit is a sinusoidal signal that tells you that there's a planet orbiting that star. The latest generation of these spectrographs can measure really precisely what that wobble is, down to about 2 meters per second for my survey. And they're trying to push down to what it would take to detect Earth's motion, which is about 0.2 meters per second around the sun. But my survey would be able to find things like a Neptune size or super Earth sized planet. So I'll talk first about this project to search for exoplanets orbiting white dwarf stars. And to use this, we combine a lot of data. First of all, there's a space telescope called Gaia that has imaged most of the stars in the Milky Way very precisely. And using the data from Gaia, we can identify which stars are white dwarfs. So there's a catalog of all the white dwarfs nearby in the Milky Way. I wrote a proposal, and my advisor has written other proposals to look for planets around those stars using this test space satellite. Should we find a good candidate planet by looking for periodic signals, we can actually confirm that using these modest-sized local telescopes to confirm from the ground that that signal is truly a planet as opposed to some kind of systematics on the spacecraft. And if we were to find a planet, it would be an excellent candidate for James Webb Space Telescope to study the atmospheres because of the properties of a white dwarf star. So what are white dwarf stars? These are stars that are at the end of their lives that started out as a medium-sized star, similar size to the sun. So if we look at the sun's lifetime, it's about 4.5 billion years old now. It's in the middle of that main sequence where it's just chugging along, fusing hydrogen into helium and other elements. And it has a very stable, long life during the main sequence. Towards the end of that, it will expand up into a red giant as it starts to burn heavier and heavier elements. And then eventually, the red giant will lose most of its mass outside of the solar system through stellar winds. And what remains is a white dwarf star, which is really the core of this the star that was initially there. And an interesting fact is that almost all of the known planets that we have found are orbiting these main sequence mid-sized stars, which will eventually become white dwarfs. What we expect, because of the expansion into a red giant, all of the inner planets would be consumed by the star. And then when it loses a lot of mass, that throws any remaining planets into kind of chaotic orbits where a lot of stars may either fall, a lot of planets may either fall into the star or be lost from those solar systems. So we might expect planets to be rare around white dwarfs. As I mentioned earlier, we've discovered one transiting exoplanet using the TESS Space Telescope before I started my my PhD degree in 2020. And in the middle of this slide, it shows that system to scale. One thing about white dwarfs is they're very dense. They have about 0.6 the mass of the sun packed into the radius of the Earth. Since they're such small stars, when a planet like this one that's about the size of Jupiter transits in front of it, it blocks all of the light from the star. And if you were watching the star, it would disappear for about 10 minutes. Since it's also so very small, it means that the habitable zone, which is the area where liquid water, the temperatures are right for liquid water to exist on the surface of a Earth-sized planet, that is actually inside the orbit of this planet, which has about a 1.4 day period. So this star is putting out a lot less energy than the sun, and the habitable zone, and this planet is like well inside the orbit to Mercury if it was in the solar system. But as I mentioned earlier, because the star is so small, you'll see a very deep transit blocking most of the light when a planet goes in front of it. And I started this project because if we can find one Jupiter-sized planet near a white dwarf, well, there just might be an Earth-sized planet that could have moved into this habitable zone at some point near the end of the star's life, and there could be life on such a planet. One of the things that really hooked me onto this in 2021 is I was just starting my observing with CCD cameras, and we looked at one of these. This is a binary star with a red dwarf orbiting a white dwarf. And what you'll see in this little movie is this planet just above the red plus sign. That star will be blocked by the red dwarf transiting in front of it and will disappear for about 10 minutes. And that was a pretty exciting first observation with the CCD camera. And I'll start the movie now. So you'll see it disappear there in real time. That's about 10 minutes. And I've looped this around again, just in case you missed the first time. We'll see it one more time where that star will disappear. And there it goes. That's a pretty cool observing night. One of the neat things about these stars being so small is that we could actually detect a Earth-sized planet orbiting like a 16th magnitude star with this 20-second data. And in that case, it would only take about 1 minute for the planet to transit in front of the star. And this was a graph that I put together for a proposal showing why we needed that 20-second cadence data to get, it's hard to read, but a 7.5 signal to noise ratio, a true detection of that planet. So theoretically, we could find very small planets orbiting these stars. We've been at it now for about 1.5 years and have looked at thousands of white dwarf stars that we got added to TESS's, we got observing proposals to get data on all of these stars. So it's been cool, but unfortunately we haven't found any planets, which may confirm that indeed they're pretty rare around these types of stars. And we got lucky with the one Jupiter-sized planet. I'll talk a little bit then, shift gears to another survey, searching for exoplanets born outside the Milky Way. Our technology, even radial velocity observations, is such that we really can't look for exoplanets around other galaxies. But we figured out this project to look for it anyway. We called it the VOYAGERS survey, and that stands for Visions of Yore, Ancient Gaia-enceladus Exoplanet Revealing Survey. So how do you come up with something like that? Well, you take a road trip back from a conference in Aspen, Colorado, with myself and my advisor next to me, and a couple of other associates. Melinda Soares-Fuento is in the back seat there, that I think you guys may have heard give a talk recently. And one of the things about my advisor is he likes surveys named for Star Trek themes. So we came up with Voyagers and had to figure out a name that was somehow related to Star Trek. So this Enceladus dwarf galaxy merged with the Milky Way about 10 billion years ago. And this little cartoon shows that merger happening. The two galaxies had stars with different properties. And this color magnitude diagram on the right is one of the ways astronomers look at the properties of stars. And we know that that happened 10 billion years ago, not because somebody observed it, but because if you move the clock forward to present day, in the current Milky Way, we can see these two populations of stars in the current Milky Way. It's also known as the sausage. And the reason for that, so Gaia-enceladus sausage, is that one of the first researchers who was looking at data and realized there was this unique population of stars came up with this diagram on the left. And they're plotting in galactic terms the radial velocity towards or away from the center of the galaxy, and then on the y-axis, the circumferential velocity of the stars orbiting. And Milky Way stars are generally in the group circled in white there. And then there was this feature that stood out that this person felt looked like a sausage. And that's in the circled in black in this diagram. So that name stuck. And sometimes you'll hear it referred to as the sausage. The neat thing about this situation is that these are all stars from a different galaxy that are now orbiting all over the Milky Way. And the graph on the right is showing the location of the sun on a plot of just two of the dimensions in the Milky Way. So it's sort of like a slice through the Milky Way. And all these black or the blue arrows are Enceladus stars. And you can see there's quite a few of them that are in the neighborhood of the sun and therefore are bright enough for us to use radial velocity to try to look for planets around them. So we looked at a catalog of these stars and selected the best stars for a radial velocity survey based on sorting through stellar properties. And there are certain stars that tend to not have a lot of noise or variability in the data for radial velocity. They're mostly stars like the sun. And then we were also able to take a number of observations using a low resolution spectrometer called TRACE that's also in Arizona. In between those two sets of observations, we got our list down to about 140 or so stars, and then picked 22 stars for the survey. So we had to really find the best stars for the survey because we need to do 50 observations per star over about 3 years on these 3 to 4 meter size telescopes, which is a total of 1,100 observations. So it's a lot of telescope time. The plots on the right show some of the unique properties of these stars. I'll start with the upper left of the plots. This is what's called a metallicity diagram. To astronomers, anything heavier than helium or hydrogen is called a metal. So these are all heavier elements, and they measured those in abundance ratios relative to hydrogen, which is what's on the x-axis here. And then certain types of metals are called alpha metals. That's what's plotted on the y-axis. And the black points are the main sequence Milky Way stars that are in the thin and the thick disk. And then you can see that there's a different population of blue points. And in the bottom, they're just turned into a histogram that shows basically these are all metal poor stars with high amounts of alpha elements, which means they were formed early on in the universe's life. And so that's typical for these Enceladus stars. And then if you move to the lower left, you can see the 22 stars we picked out, and we specifically avoided stars that overlapped with the properties of the stars that in the Milky Way, because we wanted a clean sample of stars to look at. And we've looked at a variety of types of stars, is the basic thing you can see in the plot in the lower right. Dwarf stars is another name for main sequence stars. Towards the end of the life, they begin to evolve into subgiant and giant stars. So about half of our stars are main sequence dwarf stars. About half of them are subgiant stars. We talked a little bit at the beginning of the evening with whoever was on at that time about the telescopes I use. I mentioned the WIN telescope with the NEID spectrometer. That's the main telescope that we started the survey on. But we very quickly realized that we were going to need to expand the survey to other telescopes to get our 1100 observations. And so we're collaborating with teams using the HARPS-N telescope, which is in the Canary Islands, and a telescope in Spain that has a spectrometer called CARMENES on it. And so I'm combining data from those three telescopes. And most of these are Q observations that are done by astronomers on the mountains. And they just send the data after the end of the night, and we accumulate that to do the survey. I am going to travel to HARPS-N to the Canary Islands later this month to spend about a week being that astronomer taking those observations. And then a fourth set of telescopes that I'm currently using is Minerva Australis. That's located, those are 4.7 meter telescopes in Queensland, Australia. And the reason we're doing observations there, we're starting to try to expand our survey to stars in the southern sky. This slide will show you what some of the data that we're looking for should look like if we're successful at finding a planet. This is simulated data for a 15 Earth mass planet with about a 7-day period. And that's added on top of the noise of real observations from these three spectrographs. The plot on the left is called a periodogram. It plots the period versus what's called the normalized power, which is kind of how many of the observations seem to follow this periodic pattern. And what you see is the spike at about 7 days, just below 10 in period, is showing you that we've identified something that's very periodic. And the horizontal lines kind of say different confidence levels. And in this case, we would detect this planet with what's called greater than a 0.01% false alarm probability. So a pretty good confidence that it is indeed a planet and not some other signal. The plot on the right shows you what 3 years of data will look like. It's a time series of RV measurements that are folded on top of each other by the period that's been identified. And you can see that there's a nice sinusoidal signal that shows the discovery of the planet. So you may have seen some charts like that. And with that, that's it for my work. Again, it'll be about 2 more years of collecting data and analyzing that data to see if we find any planets. And I'd be glad to answer any questions.
Yeah, Bob, one of the illustrations you showed was a red and white binary system with the exoplanet. How common is that?
Are you saying something like this?
Well, you were talking about finding a binary system with an exoplanet. There it is. Yeah.
Yeah,
You-
so this is the binary. It's actually the red dwarf star crossing in front of the white dwarf star. And those are a lot more common than planets around white dwarf stars. What will happen is the first star will go through its life cycle and become a white dwarf. And if there's there's more binaries in the sky actually than individual stars. So towards the end of their life, most stars will be something like this. Red dwarfs they're very small and therefore have very long lifetimes. And they remain orbiting the white dwarf that's left over after a larger star has gone through its life.
Okay, maybe I misunderstood. I was thinking you were saying that there was an exoplanet in that system.
Yeah, no, it's just a good example of what a transit looks like around a white dwarf.
Got it. Okay, I do understand that they're when you were saying you were looking for unusual exoplanets, that they have seen some binary systems with exoplanets in it. They found I thought they found a couple.
Yeah, there are some distant binaries where one of the stars has planets. And then there's also just a handful of circumbinary planets that are orbiting a binary pair of stars that are very close together.
Yeah, I was reading something online too about that there's theoretically a trinary system that they're finding exoplanet in too, a large exoplanet, that there was evidence for it. And that kind of goes to a lot of science fiction stories like Three Body Problem and Star Wars with Tatooine.
Yep. It becomes more difficult to find those planets. Most of those would be found through transits. But deciphering what that signal looks like, most people do what I've done, which is you try to look at the easiest stars to find planets around first, and then expand your population.
Gotcha.
Good question.
Does anybody else have a question for Bob? Well, thank you so much, Bob. I think I really got I don't know about anyone else, but I think I really got a great understanding and feel for the work you do. And this is some really neat stuff as far as, I think I've been in the club for a while, and I think that's not something that we think about, that, our galaxy has in fact merged with another galaxy in the past. And it's such a great, neat concept to think that you could